Good afternoon, everyone. This is Sadia Zafar from HRAI. I would like to welcome you to today's session on highly efficient, high-temperature hot water CO2 heat pumps brought to you by Mitsubishi Electric Heating and Cooling. Our presenter, Gary Chang, Applications Engineer at Mitsubishi Electric Heating and Cooling, will discuss efficient hot water heating with heat pump technology that utilizes CO2 refrigerant to supply high-temperature hot water. You will notice on the control panel of your screen, the Q&A feature. Please use the Q&A feature to ask your questions at any time during the webinar. They will be addressed at the end of the session. Also note, this webinar is being recorded and the recording will be sent to you following the session. Now we welcome Gary. Gary, if you can unmute yourself.
Thank you, Sadia. This is Gary from Mitsubishi Electric. How are you doing? So you guys can hear me okay?
Yes,
Sadia?
we can hear.
Okay,
Yep.
Perfect. So like I mentioned before, good morning, good afternoon, or good evening for those who's turning in through a webinar. Thank you for joining us today. Thank you for joining Mitsubishi today to discuss QAHV hot water heat pump. And then thank you for HRAI for inviting us to give a webinar, a presentation for today. So for today's session, we'll be discussing, or rather, we'll be introduce you to the upcoming QAHV, which is a CO2 hot water heat pump system to create hot water to fit your needs. So along with this introduction, in the future, when the product is available for Canadian market, we will also be launching training seminars for design professionals, for contractors, for installers, and then as well as sales webinar for those who are interested in the product to dive a little bit of deeper into the product feature and function. So today we're just giving you like a brief introduction on the QAHV system, feature, benefit, fit, form, and function. So what is QAHV? Why do we feel it's important to introduce it to the Canadian market? Because we feel it is an ideal solution for hot water generation. It can create high temperature of hot water, and because it's utilizing CO2 refrigerant, so it is considered a low carbon solution. It can be used for where you need a lot of hot water or high temperature hot water, for example, healthcare, hospitality sectors, education, schools, institutions, aged care facility, long-term care home, residential or commercial building. Whether it is in winter, whether it's in summer, we always need hot water throughout the year. So this unit is, so we feel it's a good fit for our market as well when you are looking, when the demand for high temperature hot water is high. So some of the key advantage of using the Mitsubishi hot water heat pump system. So it is a powerful and incredibly efficient by adapting our Mitsubishi unique patent technology. So it is reliable performance. So it can also help to achieve our mission, as in Canada's mission of achieving net zero emission by 2050. So it is high efficient, so it can generate or high efficiency up to 4.11 COP. So 1 kilowatts of power input can generate up to 4 kilowatts of heating output. It is utilizing CO2, which is R744 refrigerant with a global warming potential of 1, and it is also a natural refrigerant that we can source. It uses patent technology, unique twisted and spiral gas cooler to enhance the energy efficiency. And more importantly, it can operate down to minus 25 degrees C. So this unit is not only high efficiency, also high performance, as well as high quality, because it also have low noise sounds for superior performance. So this is really a high performance product to suit your needs. So CO2 is a clean and green natural refrigerant. So we are able to generate hot water without any compromise. So we are using R744 as a refrigerant, which has zero ozone depletion factor of 0, as well as global warming potential of 1, which is help to reduce the CO2 emission by creating hot water. So it is helpful to use it for healthcare, right? So hospitals where you need hot waters all day, throughout the day, hospitality, hotels, restaurants, aging long-term care home, or even educational institution where, a school, they can take advantage of the hot water generation because, like what I mentioned earlier, we will need to use hot water throughout the years, all day, all month, and then all year. So in here, this is an interesting study done by NRCan. So you will see this is taken by nrcangc.ca. This is their study, and they found out that Canadians using about 75 liters of hot water for each home every day, washing the dishes, cleaning, and showering. And this study is actually done in 2017. As you can see, the source from NRCan is actually from 2017. So that is before our pandemic. So, and then during this pandemic, because people are working from home a lot more, so the hot water heating is most likely to go up as well. And because, and then there's also a similar study, but it is done in 2003, done by NRCan, to talk about hospitality sector and their energy usage. So on average, in that study, again back in 2003, in the hospitality sector, hotel use about 15% of its total energy for hot water. And in full-service restaurant, it is about 50% of energy use is used to create hot water. And then let's say even for fast food restaurant, it is about 8%. Therefore, you can see during this pandemic, post-pandemic, for sure, the hot water demand will go back to its original or even increase as the time goes by. So we can definitely take advantage of QAHV to generate hot water to not only reduce the carbon footprint and also reduce the energy consumption and energy use compared to, I guess, a more conventional system and equipment. So how does hot water heat pump work? So very similar to other type of heat pump technology or other Mitsubishi heat pump technology or heat pump technology in general. So you apply let's say you apply a kilowatt of electric energy, and the heat is actually being absorbed by the energy from the surrounding air, and then it's drawing and then creating heat to heat out hot water. So you can see, like what I mentioned before, is the unit, our QAHV can generate or has a COP up to 4.11 based on a specific testing condition. So you can see that it's highly efficient. We're drawing, let's say, 1 kilowatts of electric power, and we are able to combine with the heat absorbed from the energy from the air. We're able to achieve, let's say, 4 kilowatts or even, to create a COP of 4. So it also, so how does it actually work and why does it make it special? So first of all, it is utilizing a special or a unique CO2 inverter compressor from Mitsubishi. So it is able to ramp your power up, ramp the capacity up and down depending on what is the requirement and also on the outdoor condition. Along with that, the unit comes with an inverter-driven fan that can spin depending on the wind speed and depending on your outdoor condition, right? If it's a cold, windy day, or a hot, windy day, hot, humid day, or maybe a mild, windy day, the fan can be ramped up and down depending on what's required on the condition, as well as the compressor can ramp up and down depending on what's required. And on top of that, Mitsubishi, we introduced this unit equipped with a twisted spiral gas cooler pipe. So you can see the water is flowing in the middle of the pipe, and around the water piping, there is section of the twisted pipe, a spiral refrigerant piping. So increase your surface area, which increase rate of heat transfer, and therefore it increase the efficiency of the unit. As you can see, there are 3 contacting points, the 3 contacting surface. So that's why it was able to reach that that efficiency throughout just by increasing the surface area. And on top of that, we like to have turbulent flow, so the water and the refrigerant is actually being properly, the heat is properly transferred throughout the unit. So why are we using the gas cooler? Because scale will grow when the cold water is heated. So the gas cooler is using a larger diameter water pipe. So scale is accumulated on the pipe, is less likely to result in the pipe clogging. And because CO2 also operate at a higher pressure, so round refrigerant piping with thick wall will probably increase the internal pressure. So again, increasing internal pressure may result in not so efficient in such a way. Therefore, we introduce the twisted pipe around the water piping with the spiral piping. So increase your contact area between refrigerant piping and hydronic piping. And this also improves efficiency while reducing the product size. So in here, next, it is suitable to create hot water. So that means when the delta T between the inlet and outlet water temperature is high, the unit will really perform based on the on the COP level. So you can see here outdoor temperature, let's say 80 degrees C of dry bulb, and then you have water entering the unit at the water entering the unit is about 15, 20, and then with the delta T of 50 degrees Fahrenheit, we're able to create a COP of 4.11. So the COP is, and that's where it really accelerated. So very high COP when you have a large delta T, and then it is suitable for a sanitary hot water supply along with others. But the easiest way is perhaps, let's imagine you have hot water cold water from the city starting at, let's say, 10 degrees Celsius, and the unit will be able to boost it all the way up to 70 degree or even 77, 80 degrees C, depending on the usage. And we are able to, and then while maintaining that high COP level of 3.83, 4.11, depending on your delta T and depending on your outdoor condition. So you can see here, here's some basic information on the QAHV. So first of all, it is utilizing a CO2 refrigerant, and the nominal capacity is about 136 MPH or 40 kilowatts. The outlet water temperature can be between 46 to 80 degrees C, and it will operate between minus 25 to 43 degrees C. So suitable for our climates. And you can see you can reach the COP of 4.11 if you have an entering water temperature of 20 degrees C and an outlet water temperature of about 48.9, 50 degrees C, or let's say 120 degrees Fahrenheit. So the COP will be able to reach 4.11. And you may ask, well, what about the COP when outside temperature is maybe at 80 degrees Fahrenheit, right? And then if the inlet temperature is at 21 degrees C and the outlet at 65 degrees C, the COP can even reach up to 3.83. So it is still it is a very high high performance equipment. So furthermore, here's a colorway view for the product structure. So components such as pumps, compressor, control box are all can be accessed on one side. So you are able to open the panel and then access the water inlet and outlet, drain pan, pumps, compressor, control box, and all that all can be serviced on one side. The unit does come with an internal built-in pump that can regulate the water flow based on the requirement. So requirement, for example, what's the heating load required on the other side to heat up hot water. And also, to heat up cold water. And then also what is the capacity requirement at that temperature, right? Or the unit, the fan and the compressor and the pump can ramp up and down depending on what is required based on your configuration, installation, and all that question and all that concern. And the next question is, well, the unit, how heavy is it? It's about 895 pounds. So you can see that's the overall dimension. So you can see high, 70-inch high, or plus the height of the fan. And the width is about 48 inches, and the depth is about 29 inches. So very compact. And then you can you can modulate it and place it on the on top of the roof, and then place it then side by side with each other. And you can see the service space is really not that much. It's a very minimum service space. Front of the unit, back of the unit, side of the unit is all being very, very small. However, one thing I always bring it up is so the service space in the manual is always the minimum space. So I always recommend it to go a little bit higher, right? So just because, not just because of installation, you also have to think about future service and inspection, and then also clean the coil, right? And then you really have to think about, do you really have the, can you reach it, right? Is 50 millimeter really that enough, that big enough for someone to reach out and will clean the unit properly? The answer is yes, but you really have to think about the people, right? I imagine the coldest night and someone is carrying out a heavy bag and try to do a service unit. So think about the installer as well. On the side, you can see the water. On the water, you can see the maximum piping length between the condenser, not the condenser, the water heater and the tank can be up to 196 feet, so 60 meters apart, depending on how it's being installed. And then the unit can have a certain external pressure for its heat exchanger, for the pipe to overcome, and while maintaining the GPM, maintaining the flow within the unit. So this is just a brief overview, a general overview of how the unit can be installed and what is the maximum pipe, and then depending on a location. And sometimes you also have to consider gravity, and then how you can take advantage of gravity to flow to make sure you have the water flow in and out of the unit, and also in and out of the tank. So here is a couple more example on the QHV on the installation side. You can see if it's installed by itself. Again, the installation space or the service space, the minimum requirement service space is very small. So it means you can be installed in a very small space, right? And then you can also stack, or you can also join them together in a modular combination. So you can have side-by-side installation and consider one entire system as up to 16 units all installed together. However, you really have to, while doing the design, while thinking about the space, you want to make sure there are proper airflow around the unit, so there's no short cycling of air. So basically, the QAHV is gonna take the heat out of air, right? So it will be essentially hot air goes in and cold air comes out, And then if you have obstruction and then or improper airflow, you may short cycle in the cold air, and then eventually it's not your performance may not be as well as expected, just because the airflow is not being properly distributed for the condenser for the refrigerant to suck the heat out of air. And again, the next thing is proper height for the unit stand. The unit should be placing on a stand, because in wintertime, there may be ice or snow accumulation, especially if you install that on the outdoor installation. You may have ice and snow accumulation, and we want to avoid that. So you really have to specify a proper height for the unit to be placed above the local snow line. And lastly, the proper service space, as I mentioned before. So everything you see here in the installation manual is really the minimum requirement to have the unit to perform properly. But you also have to think about the people that's actually installing it and actually service the unit, maybe leaving a few inches extra so they can reach out to and have proper space to install and service the unit or clean the coil at least. So some additional feature, you can see just a general view overview. We can have multiple module combination, so you can up to 16 units. So each unit has a nominal capacity of 136 MPH. So up to 16, so 136 multiplied by 16. So you can have about 2.1 a million BTU of total heat. High capacity per module. So under the condition or in summertime, the unit can actually operate up to 190 MPH of hot water. 190 MPH of heating capacity. Depends on its mode of operation and also the condition. It utilizes natural refrigerant, as mentioned before. It uses CO2 with the global potential warming potential of 1. So compared to other type of refrigerant, it is it's very good, very environmental friendly, and it has high efficiency. It can be 4.11, right, depending on your application. And actually, the CO2 can also reach up to 3.83 when your inlet is 21C and your outlet is 65C on a typical hot summer day of 80 degrees Fahrenheit outside. So you can supply high temperature of hot water up to 80 degrees C. So it can operate down, and you can operate down to minus 25 degrees C. And you can also have BMS connection to control it through Modbus or through external signal, 0 to 10 volt on and off, and then temperature design. And then we're going to go through it a little bit more detail in the upcoming slides. So here is the typical schematic for we recommended or we suggested. Of course, the possibility is endless depending on how you wish to do it. Because for QHV, simply put, cold water goes in, hot water comes out, and then you can utilize that hot water. It can be bringing it from 10 degrees C all the way to 80 degrees C, or 21 degrees C all the way to 65 degrees C. Right, 15 degrees C all the way to 60, 65, depending on your usage. So here it's just a very basic idea to introduce the concept for domestic hot water. So you can see a basic schematic is usually, let's say, on the primary circuit, that means that's the QAHV circuit. So it comes with the built-in internal pump to regulate the flow and then to meet the capacity. So, and then as well as the set water temperature. So let's imagine you have 15 degrees C of cold water goes into QAHV, and then you are creating, let's say, 70 degrees of hot water coming out on the left-hand side of the heat exchanger. And then on the right-hand side of heat exchanger, let's say you have 10 degrees C of city water mixing with your the water from the inside the storage tank. So it may be 10 degrees C, goes into the indirect heat exchanger, and then you can be 65 degrees C coming out of the exchanger into your tank. And then from the tank, you may be applying 60 or 65 degrees C, and then mix that with the inlet water from the city to create maybe, let's say, 45, 50, 55 of hot water, depending on your local jurisdiction on where, and then deliver hot water for, let's say, shower or faucet for domestic hot water usage. So in here, just a general overview from Mitsubishi, you will be able to get requirement or minimum is the QAHV, obviously the hot water heater, and also the remote controller and the sensor and the secondary circulation kit, the temperature sensor and flow sensor, just to make sure there's proper water flow around the unit, right? So you can set the living water temperature from our part W31 controller, and you can also measure the cold and hot water from the other side, along with the flow to make sure there's no dry flow or dry run in the hydronic system. And there are some field supply parts. So for example, hermetic type of storage tank. So obviously the tank needs to be airtight, right, to store the water, and then you insulate it so it is properly retain the heat. And because the QAHV doesn't come with double wall heat exchanger, so so you will still need to have a heat exchanger, a double wall heat exchanger, and then somewhere to make sure there's no contamination by coal, and depending on where you are, some of the local requirement may be slightly different, but usually in general, I believe most of the jurisdiction in Canada will require double wall heat exchanger for domestic hot water. And then we, in the upcoming session from Mitsubishi, we'll be able to dive in on how to design the heat exchanger within the unit, and then based on what's requirement on the QHV side. And third is the pump, right? So pump, obviously you need to pump the water, or the water can be, it can be a valve if the pressure from if you have a low-rise building or low usage of just for whatever reason, you don't have a domestic cold water booster pump, then maybe there's a valve that you can utilize, and then to on and off just to make sure there's also no dry run. So pump, valve, that will be based on local procure part. And obviously, as water or most of the stuff in life, as water being heated, it will expand. So we need to provide, or the designer will need to design an expansion tank or specify an expansion tank to accommodate for the change of water volume. And along with other components, mixing valves, faucet, right? And then the shower head and all that stuff that needs to be procured locally, and then yeah, to meet code. And I think most of us will need to select, let's say, a shower head that is high efficiency, or is a certain, I believe, 2.5 GPM or 3.5 GPM. I cannot recall, but that is the specification for a shower head to come. Yeah. And next, let's talk about the next part is the storage tank capacity. So a lot of time you may ask the question, well, how big of tank you need? That really depends on what is required, and there is a general rule of thumb and then general design specification. And there are also a lot of resources online to help you determine how much hot water storage tank is required. So let's say for a hotel, right, or even for, let's say for apartment, you will need about 150 liter to 300 liter per household per day. And the maximum of hot water requirement is about 50 to 100 liter per household per hour. And then continuous runtime, maybe 2 hours. So imagine it's a condo building, apartment building, and then so everybody take a shower from, let's say, 6 o'clock to 8 o'clock, right? Maximum time so they can leave. Or same idea for a business hotel, everybody taking shower from 7 o'clock to from 7 o'clock to 9 o'clock. So that's where you will need the most hot water usage. However, for the rest of the day, you may not require instantaneous or as much hot water as required before. So you may be able to utilize some of the energy conservative strategy, or such as low shifting or low leveling, right? That to reduce your peak demand in kilowatts, right? So if you know you're gonna use the most hot water from 7 to 9 o'clock, and then in Ontario we're using a kind of day electricity usage. So maybe you can spend the hours that's off peak to create hot water and then store them in the hot water tank, and then to reduce your peak load. Or you should purposely shifting your load between hot water generation and perhaps your air conditioner, so they are not running at the same time. So let's say 12 o'clock, right? You literally anticipating creating enough hot water for washing the dishes or preparing food, and then doing let's say 12 o'clock or 11 o'clock to 3 p.m. That's where you require the most AC. Then maybe you can shift the load to reduce your peak demand in kilowatts, or you can take advantage of time of use electricity by storing or by utilizing a thermal energy storage strategy. And then there's an example here you can see for hospital, for a sports facility, let's say a gymnasium or a YMCA, if you may, right? Or city hotel, you can see the hot water it's not a flat line, just like throughout the day. So there is a certain period that people will use the most hot water, and then we'll be able to take advantage based on different study and different run. And then we are able to cooperate what you can see on the bottom right-hand corner. You say how much hot water is being produced and how much hot water is being consumed. And then what is the status of hot water inside your tank to accommodate for the load. So here are some of the control options, or some of the basic information on control for QHV. So you can see, so the unit will be able to send a 0 to 10 volt signal to either open the two-way valve on different position, and then send an on and off signal to tie into the pump, or you can send a 0 to 10 volt directly to an inverter driven pump to control the flow depending on what's required. And then in here, most you can see on the top two, and then on the right hand corner, those are the single configuration for a single unit. However, if you, like I mentioned before, the unit, you can join up to 16 of this unit to create a bigger system. So because it comes with the internal pump, therefore we strongly recommend it to have each individual heat exchanger to service each load. I mean each QAHV. Just make sure the load is being the GPA is not being disturbed, and then the unit will self-regulate, right, depending on what's required, the load requirement, and then the ambient condition, right? So the unit will make the adjustment, make the decision on which unit to be turned on and on what capacity based on its own algorithm to accommodate for what's required on your hot water generation or hot water requirement side. So in here, again, this is taken from our design manual, just a sneak preview of what's upcoming. You can see most of the time, very basic, very compared to a conventional system, and then very similar. So you still need a strainer, you still need a strainer, you still need a flow sensor, you still need all that. You still need a valve, right? Temperature to read the temperature and all that, and then expansion tank, very similar. But keep in mind, the QAHV comes with own internal pump. And then in here, and then a lot of time we'll mention on the right-hand side, on the left-hand side, the unit heating circuit and the secondary heat circuit. So you will need to perhaps provide a plate heat exchanger, right? And then also all the equipment or hydronic equipment alongside with it, strainer, pumps, expansion tank, flexible joint, and then the air vent. So all that very similar to a conventional hydronic system when you are incorporate that into, I guess, a more conventional system, let's say a boiler type of situation. So in here, you can see the control of QHV. You can be single unit, external temperature sensor, and to turn the unit on and off, and then to read the thermistor, to read the temperature, and then ramp up and down based on what's required. And then it can be connected to a part W31 or a centralized controller. So we can see not only your heating and cooling from the VRF equipment, as well as your hot water system, how it's being operated at the same time through the A200, our centralized controller. And you can also connect up to 16 units. So from 2 to 16 units, you can daisy chain them, and they will be able to communicate internally from the main unit to the subunit, as well as communication between the subunit through MNET line. And then you can have dry contact to switch on and off, or set temperature, or send a signal for the unit to operate and react to what's required on the site. Besides that, there are also 3 different modes of operation depending on what's required. So let's say a maximum capacity, that is basically you just say the unit will need to run on whatever it needs to run. So just based on the load requirement, right? So based on what's required, it can be ramping all the way up to, let's say, 190 MPH, or you can just ramp up and down depending on what you need, what is required at that time, and then to react to that maximum capacity requirement. Or you can do it on the energy saving mode. So basically what's happening is at 2 degrees C or higher, so the unit will be acting constantly at 136 MPH. So you will be able to, right, as outside temperature gets a little bit warmer and warmer, so you know, you may not need as much hot water requirement as before. And lastly, the energy saving mode, the mode will be able to operate up to 136 MPH of capacity. However, reference and compared to a nominal capacity 136 MPH. So however, as your inlet water temperature decreases, right, the capacity will be increased up to 176 MPH to maintain the same level of GPN, and then to maintain the same level of your living water temperature. So basically 3 modes. One is let the unit run based on its highest possible capacity, just ramp it up and down automatically based on what's required. Or you can lock the temperature or lock the capacity up to 2 degrees at 2 degrees C and above, just to kind of make sure it is not drawing unnecessary power if not required. And then thirdly is somewhere between energy saving operation 1 and the maximum capacity, where it will be able to lock the unit up to 176 MPH of heating capacity, and then depending on what's your inlet water temperature and your set temperature, as well as requirement and the GPN. So 3 very flexible operation range for you to choose depending on what's required to achieve that extra level of energy efficiency. Just some more examples. So it can be a very simple control. It can be a non-contact input, right? On to turn on the system, off to turn off the system. So you will have, let's say, a thermistor, say the pipe, the water temperature inside the pump, inside the tank may be too low. Just turn on the QHV, turn on the pump, and then just recirculate and heat up the water to maintain that level. It can be very, very simple operation. Or you can also have a 3 sensor control, right? Because stratification does happening inside a vertical tank. So you can have TH15, 16, and 17, depending on what's required, and then turn on the unit depending on what's required on the 15, 16, and 17 on what's required to operate the unit to heat up the system. I mean, to heat out the water depending on requirement. So in here, just some example, if TH16 is too low, right, lower than the set temperature, then the unit will start, right, to heat up hot water. And when your the bottom of your tank is getting hot, then the unit will stop, right? So if based on stratification, right, the coldest water at the bottom, and which is also mixed with city water a lot of time, so you will be able to turn on and off based on that requirement. Or when if the middle of the tank is too cold, then you just want to have a proper mixing inside your tank, right? And then create hot water for your system. And then if it's very, very small, I mean, when your domestic hot water storage may be small, then, right, your stratification may not be significant. So it can also says, well, on top of a unit, if your supply water temperature or the top of the unit is too low, then start a unit. And once you fill the tank with hot water, or the hot water in the middle of the tank is meeting that requirement, then stop the unit. So very, very basic and simple design. Next question is, maybe what happens if you have more than 2 tanks, right? 2 tanks, 3 tanks. The unit you can have up to 6 sensor control per set. So, but you will need 2 or more QHV because each QHV will be able to take 3 sensors. So in here, you will be able to turn on and off depending on what's required. TH15 from the main all the way to TH17 from the sub, right? So we can see QHV is producing hot water, and this hot water from the TH15 may be directly supplied to your to the hot water usage downstream. Let's say to a shower, to a dishwasher, to a laundry machine. However, during the nighttime, you want to fill the tank as much as you can because you want to offset your the load in during the nighttime. So you fill the water, and the unit will be on and off depending on your sub thermistor and temperature sensor. So here is just another example. The QHV can also take 0 to 10 volt and then send a signal out to control your external pump, depending on what's required. And depending on what's required, you can also recirculate your water temperature on the other side. So you can have field supply, analog output, input, just to make sure there's no dry run in the system. Another example here, you can see with more than 1 QHV, because QHV already has an internal pump, you can also send an analog signal to each pump just to turn on and off the unit, or it can be turned, on the secondary side, or you can be turning on and off, or turning modulating a valve to see what's required on that side as well. On the requirement side. And thirdly, if you can, here's another example, really depending on what's your requirement. So sometimes you have, let's say you have a low, you have a high. So sorry, yeah. So let's say for on the top of the picture, you may be using a mixing valve, and then you're having a recirculation pump just to recirculate the water because the load may be low. The hot water demand may be low inside the building. So you are able to, and then due to stratification and due to hot water low, you are able to maintain your TH15 on the hot water side on the main unit. So you don't really need a secondary heater because your recirculation water from your building may be able to dump into the tank. And then, so let's say 60 degrees C of water leaving your the tank, and then after you travel through your building, maybe it become 58, 59 degrees C, right? And then you dump it into the tank, mixing with 65 degrees C of water, maybe it's be able to maintain that 60 degrees C, and then into your the pipe. I mean, into your domestic hot water usage. And then here's just example. I'm assuming this hot water tank is actually double wall, so that's why there's no double wall heat exchanger in the middle. But this is just a demonstration only. And on the bottom of the image, you can see on the bottom of the picture, there is a reheater. Just in case if you are low, it's actually low, and then for longest time, and then your hot water tank is essentially full. You have a large building, so the 60 of water that's traveling all the way throughout your high-rise building, and then or a poor insulation, this 60-degree water may become, let's say, 55 going back in. So you really do need to bring it all the way up to a little bit higher, right? Just to meet codes and your local jurisdiction that really require. And then if it's a poor, maybe this, for some reason, this heater needs to be sized. So that's something to look into or evaluate it. And then just because your hot water load inside the tank is lower than is not very high, so you will be able to incorporate the heater on the other side as well. But again, that is based on what the designer's preference is. And lastly, some of the anti-freeze system, because again, we are in Canada, so it's not always above zero. We don't have a weather like we have here in Ontario today. Lots of sunshine, nice and warm weather. It does get cold. So the unit also have a function to circulate the water to prevent freeze inside the water heater or inside the QHV. So basically, the pump will run to prevent freezing when the outdoor temperature is 1 degree C or less, and the inlet water temperature is 3 degrees C and less, right? And then, however, pump will be off when your outdoor temperature is 3 degrees C or your inlet water temperature is 5 degrees C for more than 3 minutes, right? That is just to recirculate, just to make sure the water does not freeze inside the heat exchanger and does not freeze inside the unit itself. And on top of that, I think a lot of us are very familiar with the concept of heat trace, right? So, especially I remember the cold weather, let's say in like in the colder region. So we will wrap the pipe around, wrap the heat trace cable around the pipe, around the joint, just to prevent the water from freezing. So, and then this, and then there's also self-regulating cable that you can, the resistance bracket or heat capacity will increase or decrease depending on your pipe temperature, right? The touching surface temperature to increase or decrease and to keep the water from freezing. And also you want to make sure the joint is above 0 degrees C. So last but not least, just to recap, the QHV N136TA HBB. So it is now available in our market as of now, but it will be released in the near future very soon. And then we'll be able to go into a more in-depth analysis, introduction, and what we talk about it today. Unfortunately, I only have less than 1 hour. Otherwise, I'll be able to talk about this product for 2 hours, 3 hours, depending on what's requirement, feature, benefits, fit, form, and function to make sure the unit is designed and installed not only functional but also reliable for many years. So just to recap, the unit has multiple module combination. It has high capacity per module. It can actually go, while the nominal capacity is 136 MPH, it can actually go up to 190 MPH, depending on the condition of the site and depending on how you designed it. You utilize natural refrigerants such as CO2. So very low global warming potential, which is 1. High efficiency, you can achieve a COP of 4.11. and then if, based on the inlet and outlet water temperature, as well as your ambient condition. We're able to supply high temperature of hot water up to 80 degrees C, and it can even operate at low outdoor temperature at minus 25 degrees C. And then we are able to incorporate that with external control through 0 to 10 volt, through on and off signal and all that. So that's it for me. And then I see, yep, so go ahead.
Hi, Gary. It's Loretta Zeter from HRAI. We have some questions for you, actually quite a few. So this was obviously a topic that piqued a lot of people's interest. So I'm going to read out the questions, and if anyone who'd put in a note where they had some questions, if you want to actually verbalize your question, could you just put into the Q&A that you'd like to ask your question verbally? I'll just start things off. We had one question, actually I'm not too sure who it was from, but they're asking, what are approximate lead times for the QA-HV units?
So at the moment, it is not available. QHV N136 is not available for Canadian market as of now. And then everybody, I can see the participation of 106 people. And then, so obviously we'll inform the market when it's available. And then we are actually, so today is really just, today is just an introduction to the market to get everybody familiar with the product. And then the lead time, I'm not really sure at this moment, but we'll inform the market as soon as it's available.
Okay, I have a question from Christopher, and I'm going to unmute you. Christopher, could you ask your question?
Sure, I actually have a few of them, but I'll start with one. Is this something like, I'm curious about the operating refrigerant pressures, and is something that the local refrigeration techs will be able to work on themselves? And if so, are they going to need special tools and training?
So that's a good question. This is, I am not a refrigerant tech myself, but from the feedback I hear is we are also working on a training session to make sure this unit is properly handled for the service technician. And also, so that's, and then we're evaluating, and then we are working with some of the certified refrigeration technicians here in the office to make sure it's being handled properly, right? So, so install it properly, design it properly, and then install it properly and safely is very, very important. And then and just to make sure the unit is reliable and then functional. So right. We'll talk. And then again, we are also in the we're also in CSA B52 and also with some of the CSA committee. So that's something that we'll for sure discuss in the meeting as well, just to see what will be a necessary step. Yes.
So the support concept involves local maintenance, if we including refrigeration work at the local level. And I ask that because I know that typically the pressures are 6 times higher than most, like
yes.
R410A.
Yep.
Yeah, okay. Am I allowed to ask a second, or shall I?
Go ahead. Go ahead. Yeah.
Okay.
Go ahead.
So, do you know what is the maximum entering water temperature for the gas cooler? Does it have to stay below, say, 30 C or whatever for the gas cooler for carbon dioxide?
So the it's from our document, you can actually go up to like 49 degrees C. So it can go. It's not only for like 10 or A or 20 degrees C. You can actually go to, let's say, 49 degrees C, right, or 120 degrees Fahrenheit. However, during that time, if you are just the nature of the gas cooler, if your entering water temperature is, let's say, above 29 degrees C, then your COP will really drop because it's not properly being cooled. right? So you will derate the performance of the unit. However, on the other side is if you really have a 49 degrees C of entering water, then you also don't need that much capacity to heat it up to 70 degrees C compared to heating out water from 10 to 70, right? So, yeah, so I think 49 degrees C will be a good a cap for the upper limit.
Great.
Okay.
Thank you.
Okay, thank you. I've got quite a few. If we don't get through all the questions, Gary, do you mind if I sent you a list and you could answer the questions and we can send it out to this group? Is that possible? Yes. Yeah. Okay.
Yep,
so I'm just going to
sure.
go through. I'm going to go through a couple of these. I had somebody ask, what does COP stand for, and how is the how is the water kept from freezing in the wintertime?
Yes. So COP stands for coefficient of performance. So basically how much heating output compared to versus what's the kilowatt input in terms of electricity. So so let's say 1 kilowatts of power consumption to generate 4 kilowatts of heat, that will give you a COP of 4.
Okay. Okay, I have another question. What are the approximate lead times? Oh, sorry.
Oh yeah, we have
I don't know. I already did that one.
Yeah.
Sorry. What
Yes.
type of refrigerant pressure are we looking at here?
I don't know on top of my head, but I know it's like mentioned before, it is a high pressure compared to a conventional refrigeration system. Let's say a R410A, R47C, R134. So it's a little bit higher. Not a little bit, it's a lot higher. But I don't have that value on top of my head.
Okay.
Yes.
What is the lowest or maximum delta T the unit can operate at?
So the unit is from our factory data, the entering water temperature can be 49 degrees C, right? And then you will still produce hot water at 70 degrees C. So delta T is living water temperature versus entering water temperature. So 70 multiplied by 50, so 20 degrees C. Yeah, that will be a really good cap on the unit. And on top of that is let's imagine we are doing the doing the installation like this. What you can see, there's a heat exchanger. So remember, QAHV has internal pump built in to regulate up and down depending on your entering water temperature and your outlet temperature to meet your delta T. Yeah.
Okay. I have two questions here. What about freeze protection for the water inlet? You might have already actually answered that one.
Yes.
And then another one, can it replace a home heating boiler?
So usually when people say home heating, again, for my so short answer is yes, but the long answer is the unit require 208 3-phase. Okay, so 3-phase units. So depending on your home, are you able to get 3-phase power, or are you really locked into 1-phase power, right? So if you have a big mansion, then yes, you can definitely, and then you can get 3-phase power, then definitely take advantage of this unit. But for my own self, I only have one single-phase unit, and then because I have a small house, a tiny little unit, so sometimes it doesn't really make that much sense. But yeah, we're also working on the residential products, right, with the unit. So as soon as something is available, we'll for sure inform the market.
Okay. When will the QAHV unit be available in Canada?
At this moment, let's say it will be about end of I want to say somewhere between Q3 or Q4, calendar year 2021. So that's where we are looking into and then introduce it to the market. That's as of now.
Okay. I've got one other question here. We're in the Arctic here. The system looks good for our areas supplemented with oil backup. However, because we can get to -40, I am interested to know, can we run glycol through the QAHV to prevent potential freezing of the unit?
Yeah, so at the moment, we are still looking at it very closely on the glycol performance because, well, glycol is a chemical. Sometimes if you heat it up too too much of hot water, it might disturb the water quality, and then it might not be suitable. So again, we are still looking into it. We're still studying how it's behaved based on the hot water system. So that's why at this moment, our anti-freeze method is still be you do heat trace on the water side, on the water pipes, and then also the pump will run to based on your outdoor air temperature and also your water temperature on the in the unit.
Okay.
In the system.
Okay, that's wonderful. I want to thank you so much, Gary. We have a lot of other questions that I didn't get to, and I'm just I'll send these off to you, and if you could provide answers, I will forward these to the group here. I really do appreciate your time today. Did you have any final words?
Not at this moment, but for sure we'll inform the market when the QHV is available. Not just only on the sales side, but also on the for the design professional, and then the technical professionals, installers, contractor, and then we'll make sure we are design it properly and install it properly and service it properly.
Okay. That's wonderful. Well, thank you so much, Gary. I really appreciate it. And I think everyone else appreciated your time. And if anyone wants to get into contact with Gary, the slides are going to be available in a recording. And I believe that your information was in the last slide, correct?
Yes.
Yeah.
Yes.
Okay.
If not, then I will for sure add it.
Oh, okay. No problem. Thank you so much. I really appreciate it. And goodbye to everybody.
Bye.